So, in this module we will see the different solution procedures which are used to solve the nonlinear system of discretized equation that we have obtained in our previous lectures. Okay. In particular, we will discuss about the Newton-Raphson solution algorithm, and we will also discuss two of the strategies, okay, like line search and arc length method, which are used to handle divergence of Newton-Raphson method or for special situations where the Newton-Raphson method may fail. Okay. So, in this module we will be discussing the following three topics. First, we will have a quick revision of the Newton-Raphson algorithm that we discussed in our mathematical essentials that we covered in the initial part of this course, followed by the Newton-Raphson algorithm for the discretized equilibrium equations and the discretized linearized virtual work expression that we obtained in the previous lectures. Okay. And finally, we will discuss two methods, that is line search method and arc length method, which are used when Newton-Raphson method faces convergence issue or it cannot solve a certain problem, okay, because of the peculiar nature in which the load deflection curve behaves. Okay. So, now recall that the directional derivative was applied to the solution of system of nonlinear algebraic equations, okay, as this. Okay. So, we had this system of nonlinear equations which were composed of n such equations. Okay. We had n such equations and the unknowns were n unknowns. Okay. So, x was the vector of unknowns which was x 1, x 2, x 3 all the way up to x n. So, we had n equations and we have n unknowns. Okay. Once we have this, our aim now is to find the solution of our system of nonlinear algebraic equation. Okay. Let us say this solution is x 0. Okay. Then we can explicitly write equation R 1, okay, as f 1 function of all the unknowns equal to 0, f 2 equal to 0 all the way up to f n equal to 0. Okay. Then we can take the directional derivative of the system of nonlinear algebraic equation at the solution point x 0 in a direction u. Okay. So, u is a direction in which we proceed, so that x 0 plus u will take us closer to the solution of this nonlinear set of algebraic equation. Okay. So, the change, okay, in the value of the function, okay, evaluated at x 0 in the direction u is nothing but the directional derivative of the function evaluated at x 0 plus eta u, okay, with respect to eta and then substituting eta equal to 0. Okay. So, now when we solve equation R 3, okay, so this is del by del eta of f of x 0 plus eta u evaluated at eta equal to 0, and using chain rule I can write d by d eta as d by or del by del x I and del x I by del eta summation. Okay. This is like del f by del x 1 by del eta plus del f by del x 2 by del eta plus all the way up to del f by del x 3 del f by del x n by del eta. Okay. So, this as a summation is here. Okay. So, that is what we have here? We have del f by del x I evaluated at the solution point x 0 into del by del eta of x 0 plus eta u evaluated at eta equal to 0. Okay. Once we differentiate this with respect to eta, we get our coefficient of eta here u I, okay, and this term over here is nothing but the gradient of the function f with respect to x evaluated at solution point x 0. Okay. So, the gradient of f with respect to x can be written as a matrix K evaluated at x 0 into increment or the general direction u. Okay. Now, the explicit form of this matrix, also called the tangent matrix, and evaluated at x 0 is given by del f 1 by del x 1, del f 1 by del x 2 all the way up to del f 1 by del x n. Second row is del f 2 by del x 1, del f 2 by del x 2 all the way up to del f 2 by del x n, hence so on, and finally, the last row is del f n by del x 1, del f n by del x 2 all the way up to del f n by del x n, and this matrix has to be now evaluated at the solution point x equal to x 0. Okay. And now, we can set up the Newton-Raphson iterative procedure use as following equation. Okay. So, the tangent matrix evaluated at a particular Newton-Raphson step k into the direction u equal to minus of f x k, and then the variable x is updated as x k plus 1 equal to x k plus u. Okay. And this we keep till convergence is reached. Okay. Remember, we discussed this, and we also discuss this algorithm for Newton-Raphson method for solving a system of nonlinear algebraic equations. Okay. So, just to summarize what we had discussed at that point, I have reproduced this algorithm here. Okay. So, first you have to input the function, and then you have to also input your initial guess or the solution point. Okay. And then you evaluate your function at this solution point. If you are lucky, your solution point will be your solution, but it may not be that case. So, what will happen? F of x 0 will not be equal to 0 vector, or then what to do? Then we initialize x equal to x 0 and we initialize u equal to 0, and then we set the iteration counter, the Newton-Raphson iteration counter n equal to 0, n equal to 1. We also set the maximum number of Newton-Raphson iteration. We set the tolerance for the convergence. Okay. And the residual r is set to, there is a residual value r which is set to a very large value when compared to tolerance. Okay. So, I said that time r may be set to 10 to the power 6 or something like this, which is a very high value, and tolerance we can set to a low value like 10 to the power minus 6, and sometime it goes all the way up to 10 to the power minus 27 like this. Okay. So, you can set to a really low value, and you can set residual r to a really large value, and then we run a do loop while our residual is more than the tolerance and our number of Newton-Raphson iterations are less than the maximum number of Newton-Raphson iterations. Okay. So, this is there so that the loop does not go infinitely. Okay. Next, what we do? We compute our gradient, okay, k, that is the tangent matrix at the solution point x. So, for n equal to 1, this x will be equal to x 0, and also we calculate the function f, okay, at x 0, and then we solve for the general direction u using k u equal to minus f. Therefore, u equal to minus of k inverse f. Okay. Once we have solved, we update the value. So, this is like x k plus 1 is x k plus u. Okay. And then what we do is we again find out the function at new solution point x k plus 1 and take its norm with respect to the value of the function at the start, and we then call this as residual r. Okay. And then we increment the total number of Newton-Raphson iterations by 1. Okay. And then we go back and then we check whether our r that we just now computed is more than tolerance or less than tolerance. If it is more than the tolerance value, then we repeat the Newton-Raphson steps, or our n is less than n max, okay, then we repeat the Newton-Raphson step. Okay. If either of these condition is not valid, then we come out of the loop. Okay. So, once say we have achieved the convergence within the prescribed number of Newton-Raphson iteration steps, that is, if n is less than n max, our solution is the value x. Else, if n is more than n max, we say that our Newton-Raphson iteration did not converge. Okay. Now, the point to see here is that we are interested in this algorithm in finding the root. Okay. X 0 is the final solution, x is the root of the system of nonlinear algebraic equation. Okay. However, in our previous lectures, what we have derived, we had external loads, and these external loads may be applied in certain steps. So, this Newton-Raphson algorithm that we have discussed has to be now changed a little bit. The whole idea remains same, but there will be some additional steps that may come in between. Okay. So, in the previous lectures, we had shown that the equilibrium equation can be discretized as del v, which is the virtual velocity, dot with the difference of the internal and the external forces. Okay. So, the internal forces come because of the stresses generated inside the body, and the external forces come because of the body forces and surface applied surface tractions. Okay. And then the difference of the internal and external forces, if the equilibrium is not achieved, will be equal to some residual, which is we denote by r. Okay. So, F internal is the global internal force vector, F external is the global external force vector, and r is the global residual vector. Okay. Now, because the virtual velocities in equation 1, they are arbitrary, therefore, the residual has to be equal to the difference of the internal and the external forces. Okay. Now, as you approach equilibrium, this residual, okay, so this residual vector will go to 0 vector. Okay. So, in general it becomes very small. And now, our objective of the Newton-Raphson method is to get this residual go to 0. Okay. Now, these global internal and external force vectors, which we have here in equation 2, are nonlinear functions of current nodal position. Okay. Therefore, equation 2 can be explicitly written as the residual r, which is a function of current nodal position, equal to the internal forces, global internal forces, which are function of current nodal position minus the external forces, which are the function of current nodal positions. However, in the present course, we have not considered any follower loads or any deformation dependent loads. Okay. Or no pressure loading, no follower loads. Okay. So, our external forces are not functions of current positions. Okay. Therefore, equation 3 can be written as the residual, which is a function of current nodal position, equal to the internal forces as a function of current nodal position minus the external forces. And now, see, external forces are not the function of the current nodal position. Okay. So, nonlinearity comes now solely because of the internal force vector being nonlinearly depending on the current nodal position. Okay. Now, the explicit expressions for the global internal force vector, global external force vector, the residual and the virtual velocity vectors is given by following array form. Okay. So, where each of these values correspond to the, say, the internal forces corresponding to node 1, global node 1, internal forces corresponding to global node 2, this corresponds to the external forces corresponding to global node 1, this is the residual corresponding to global node 1, and del V 1 is the virtual velocity vector corresponding to global node 1. Okay. And remember, we have total of n p number of finite element nodes in our mesh. Okay. So, these matrices, if we consider 3 degrees of freedom per node, will be 3 cross n p, okay, 3 n p cross 1. Okay. So, this is 3 n p cross 1. Okay. So, if you have 1000 nodes, these will be vectors of 1000 cross 1. Okay. Now, we had also shown that the linearized equilibrium equation can be discretized as follows. Okay. So, the discretized form of the linearized virtual work, internal virtual work expression as a function of deformation mapping and virtual velocities in a general direction u is nothing but the virtual velocity dotted with the tangent matrix times the global unknown vector, which in our case is the displacement vector. Therefore, k is the global tangent matrix and u is the global unknown displacement vector. Okay. And the form of this global tangent matrix is shown in this matrix form. Okay. So, where k 1 1 corresponds to the change. Okay. So, stiffness matrix is a change, it represents change. So, k 1 1 shows the change in the stiffness matrix, okay, change in the global tangent matrix at node 1 because of changes at the node 1 itself. Okay. So, k 1 2 denotes the changes in the tangent matrix at node 1 because of the changes in the node 2. Okay. Like this. Similarly, k 3 n p minus 1 will denote, for example, the change in the stiffness matrix or the tangent matrix at node 3 because of the change at node n p minus 1. Okay. Like this, we can compute the tangent matrix. Okay. So, many of these, the property of tangent matrix is that many of these submatrices, okay. So, all these submatrices are 3 by 3 and many of these matrices will be equal to 0 matrices because of the connectivity matrix. Only few number of nodes are connected to a particular node. Therefore, all other nodes, if there is some change, they will not affect a particular node. Okay. So, there are a lot number of zeros in this tangent matrix and this is also a very, this is a sparse matrix. Okay. Sparse matrix means close to 95 to 99% of the entries will be 0. Okay. And this is the global displacement vector that we need to find out. This is a change. Okay. So, this is a change from the current position x that will lead us to in the direction of equilibrium. Okay. And when we add this to current position x to get a new position x plus u, we hope that we will go closer to the equilibrium. Okay. So, from our discussion on the linearization process discussed in the previous lectures, we know that the virtual work expression linearized in the direction of an increment u in psi k, okay, where k denotes the Newton-Raphson iteration step, and this was given by the internal virtual work evaluated at current Newton-Raphson step k plus the directional derivative of the virtual work evaluated at current Newton-Raphson iteration step psi k, okay, and taken in the direction u. Okay. So, once we substitute the expressions from equation 1 and equation 5, okay, in equation 6 we get del v dot R evaluated at current Newton-Raphson step k plus del V dot k, that is the tangent matrix evaluated at current step k into u, and u is the change, that is we have to add to x k to get a new position, so that we can get closer to the equilibrium position. Okay. So, now taking the virtual velocities outside the bracket, okay, what we get is this term inside the bracket dotted with del v, and now because the virtual velocities are arbitrary, therefore, the term inside the bracket has to be equal to the 0 vector. Okay. So, this has to be a 0 vector, and then we can set up the Newton-Raphson iteration scheme as the tangent matrix evaluated at x k times the change u equal to minus of the residual r evaluated at x k. And once we have found out u, the new approximation for the equilibrium position can be obtained by adding u to the previous approximation for equilibrium, that was x k, and then we hope that this x k plus 1 will be the equilibrium position. If it is not, then we will again solve equation 9 with x k plus 1. Okay. Instead of x k, now we will solve with x k plus 1, and then we will get a new value of u, and this will be done till the convergence is achieved. Okay. So, an important point to now note is that in practical situations, the complete external load vector is not applied at once. Okay. So, when you see an actual case going on, the complete external load will be applied at once. However, in simulations you cannot apply this total external load at once, because you may face convergence issue, or the worst of all, you may not even get a solution. So, what we do is we apply the total load. Okay. So, this total load is applied in a series of increment, that is small increments delta F L. Okay. And the total load would be sum over all the increments of this external force L. Okay. Okay. And this n step is the total number of load increments that are applied. So, the smaller the value of n step, probably you will have more convergence difficulties. The more the number of increments, total number of load increments you take, the more will be the faster will be the convergence of Newton-Raphson method, but there is a trade off, because if you are using full Newton-Raphson method, as will be discussed next, you will have more computational effort going into each load step. Okay. So, there has to be a balance between the total number of load increments that you require and the time it takes to compute the tangent matrix in each load step. Okay. So, the value of the incremental load can vary between the load step. So, you have to note that this increment in the load step, okay, can vary between different load step, it need not be same. Okay. So, if you are finding that your convergence is very good, you may increase the load step. If your convergence is becoming bad, then you can decrease the load step. Okay. So, that is what practically many of the softwares do. For hyperelastic materials that we have in this course, the final response is independent of the number of load steps that you take. Okay. Because the response for hyperelastic material only depends on the initial and the final point, and it does not depend on the path you take. Okay. So, your response, final response will be independent of the number of load step that you take. However, for some materials, the final response may depend on the increment of load per load step. Okay. So, there are certain materials for which your response will be different if you take different load steps. Okay. That you need to remember. Okay. So, now our Newton-Raphson algorithm for the linearized equilibrium equations that we had is now given here. Okay. So, there is a more or less the idea remains same, but we add a loop over the load steps now. Okay. So, what you have to do first is you have to input the geometric details, that is the geometric data of the body, you have to input the material properties and you have to input the other solution parameters like maximum number of Newton-Raphson iterations, tolerance, you have to give the nodal coordinates, initial nodal coordinates, connectivity, number of Gauss points that you need for integration and the boundary condition, all these data have to be given. Once you have this, you initialize your solution to the initial position of the body. The external loads are initialized to be 0, the residual is made 0 and the load step is made to be 0. Okay. Now, you loop over load step because you know how much of load you want to apply and you already would have decided that you want to go for these many load step. Then according to your choice, you set the value of total number of load steps and then you loop over load steps, you compute first of all the load increment delta FL, okay, that is the incremental external load vector you calculate. Then you add the incremental external load vector to your total external force vector to get the current value of the external force vector and then you set the residual, okay, for the current load step to be equal to the residual from the previous load step. You can do it, you can set it to some other value, but we can set it to the previous value of the residual. Okay. And then we start our Newton-Raphson solution algorithm. So, this is our Newton-Raphson solution algorithm. Okay. So, while the ratio of the norm of the residual to the current external force is more than the tolerance and our number of Newton-Raphson steps n are less than the maximum number of Newton-Raphson steps per iteration. Okay. So, we need to set n equal to 1 here. Okay. And then what we do first, we compute k at the value x. Okay. And then we solve for the displacement u as k equal to minus of r. Okay. And then we update our current position as x equal to x plus u. Then what we do, we compute the stresses, we compute the global internal force vector and then we compute the current value of the residual r as the difference of the external forces minus the internal forces and then we increment n by 1. Okay. And this we do till either we achieve the tolerance, okay, convergence tolerance, or we exceed the maximum number of Newton-Raphson steps. Okay. So, if we exceed the maximum number of Newton-Raphson convergence steps, then what we do? We have to do some divergence handling. Either the Newton-Raphson is not converging, which means either it is diverging. So, then we use some divergence handling strategy, or we have to cut our load step. So, we may need to cut our total load delta F by say half or 1 by 4, whatever you choose, and then we have to redo that particular load step to see whether we achieve the convergence. Okay. And finally, when we are exhausted with all the load step, our solution algorithm ends. Okay. So, basically the Newton-Raphson algorithm is from step 3.3 to 3.4. Okay. This is your Newton-Raphson and this is the in general total procedure for solving the nonlinear response of a material. Okay. Now, there are different kind of convergence criteria. Okay. In the previous slide, we have seen we have used the convergence criteria as the norm of the residual divided by the norm of the external load vector. Okay. So, this is only one of the convergence criteria. There are some more convergence criteria that can be used, and the first one is the displacement based criteria. Okay. In the displacement based criteria, what we do? We check that the norm of the displacement obtained in the kth step divided by the norm of the displacement obtained from all the previous Newton-Raphson iterations is less than some tolerance epsilon d. Okay. If this norm is less than epsilon d, then we say the convergence is achieved. Okay. But one of the problem with this strategy is that the actual solution may still be quite far away from the converged solution, and this will occur when the calculated displacement changes very little in each Newton-Raphson iteration. Okay. For example, when you are using the modified Newton-Raphson strategy in elastoplastic analysis, then if you use the displacement based criteria, you will have solution which is far away from the converged solution, and eventually you will not get the final eventual solution. Okay. Another criteria is the out of balance force based criteria, and that is what partially we had in our algorithm that we discussed in the previous slide. Here what we do? We compare the norm of out of balance load vector. Okay. So, this is the out of balance load vector, okay, till the current Newton-Raphson iteration step, and we check that the norm of this out of balance force vector normalize by the difference in the external load evaluated at load step L and the internal load evaluated at load L minus 1 should be less than epsilon f, where epsilon f is the convergence criteria. Okay. So, in short, this is the norm of the residual evaluated at Newton-Raphson step k, okay, for load step L, and normalized by the norm of the difference of the external and internal forces at load step L and L minus 1. Okay. Again, the problem here is the displacement solution here does not enter the convergence criteria, and this will create issues in situation where the out of balance loads are very small, but the iterative displacements may be very large. If the iterative displacements are very large, this would mean that we have not yet achieved the convergence, but because our out of balance loads are very small, then we will say, if you use this criteria, we will say that our Newton-Raphson step has converged. Okay. So, again we will have a solution which is far away from the converged solution, okay, or the actual solution. Finally, the third one is the increment in the internal energy criteria. So, in this criteria, the internal energy increment, that is the work done by the out of balance forces on the displacement increment, is compared with initial internal energy increment. Okay. So, this is the internal energy. Okay. So, UK is the solution for the displacement obtained in the kth Newton-Raphson step, and this dotted with the out of balance load, that is the residual obtained till the previous Newton-Raphson step, okay, divided by the reference internal energy increment, and if this is less than a tolerance epsilon E, then we say our Newton-Raphson has converged. Okay. Now, you can see here both the displacement as well as the residual load vector enter into the convergence criteria, and therefore, since the displacement as well as the out of balance loads both enter the convergence criteria, therefore, this kind of criteria is most commonly used in the finite element literature. Okay. So, you may well use this criteria along with the previous two criteria to have a more robust convergence criteria. Okay. So, as a note, more discussion on the effect of the convergence criteria can be found in the work by Bathe and Cimento in this particular journal paper. Okay. So, you can see this journal paper and you can have more discussion on the convergence criteria used in the Newton-Raphson algorithm and their effects. Okay. Now, we mention some of the salient features of Newton-Raphson algorithm. Okay. So, the order of convergence of the full Newton-Raphson algorithm is quadratic, that is, it is 2 near the solution. What it means is, if the error at step k of the Newton-Raphson iteration is epsilon, then the error in the next step will be epsilon square. Okay. If you are near to the solution, the error goes down quadratically, okay, that is of order 2. Okay. However, if you are using the modified Newton-Raphson algorithm, this will be less than 2. Okay. So, the order of convergence for modified Newton-Raphson method is less than 2. Okay. Then full Newton-Raphson method generally takes far lesser number of iterations to converge to the solution as compared to the modified Newton-Raphson algorithm, and also full Newton-Raphson method is more accurate than the modified Newton-Raphson algorithm. Okay. So, in modified Newton-Raphson algorithm, what we do? We are, if you remember, we discussed this in our mathematical basics, that in modified Newton-Raphson method, the tangent k is kept constant. Okay. So, evaluate it once at the start of the Newton-Raphson iteration, and we keep it fixed for all the Newton-Raphson iteration. In full Newton-Raphson method, at each and every Newton-Raphson step, we recalculate the tangent. Okay. Therefore, because we have a fresh tangent at every Newton-Raphson step, iterations needed to converge are lesser. Okay. However, full Newton-Raphson algorithm is computationally more expensive per iteration as compared to the modified Newton-Raphson algorithm. This is because in each step we have to recompute the tangent matrix k in full Newton-Raphson method, and computing the tangent matrix k is a computationally very expensive process. Okay. Therefore, full Newton-Raphson method is computationally expensive per iteration. However, note that we need fewer number of iterations per step for full Newton-Raphson method. So, there is always a trade off whether to use full Newton-Raphson or modified Newton-Raphson. So, there are strategies where once we find the convergence has slowed down, we can in between recompute the tangent matrix to accelerate the convergence. Okay. So, they are called hybrid Newton-Raphson algorithms, okay, which are in between full and modified Newton-Raphson algorithm. Okay. Now, the Newton-Raphson algorithm may face convergence issues during complex deformation process and loads path. Okay. Then what will happen? We will have to use methods like line search and arc length methods to improve the convergence rate, or to prevent the failure of the Newton-Raphson algorithm altogether. Okay. So, in actual practical situation, you may have Newton-Raphson method behaving erratically, like it will diverge, which means the error instead of decreasing, it will increase, or because of a certain type of the nature of the load displacement curve, the Newton-Raphson method may actually fail altogether. To prevent this, we have to use what is called the line search method or the arc length method. Okay. So, next we discuss what is the line search method. Okay. Thank you.